Welcome back. This is the day the Lord's made. Let's rejoice and be glad in it. I'll spend a lot of time talking about color addition and color subtraction and what we see. So this is a DC Physics Unit 5 topic. So again, what you see comes down to what light actually enters your eye. So right now, I'm being surrounded by a ton of photons just coming in and hitting me. And my brain interprets what I see based off the photons that are coming through my eye. So when you look at something, what you're seeing is really the combination of all those photons. And so when you see white, you're not really getting white photons because there's no real white photon. Instead, what's happening is my brain, if I see white somewhere, it's saying I see a lot of the colors. And so the presence of all the light. Now, however, we don't actually need all the light. We just need to have it separated into a large spectrum. So again, if we think about the rainbow, red, orange, yellow, green, blue, indigo, violet, as long as our brain sees the light from every single part of the spectrum, so if it sees stuff from the red side, stuff from the blue side, stuff in the middle, like the green, it says it's white, which makes those the primary colors. So again, as long as someone sees red, blue, and green, they'll see white light. So red plus blue plus green makes white light. So on my computer monitor, as I see white, on the computer monitor, it's generating red light, green light, and blue light coming out towards me. And so the complementary or secondary colors would be yellow, magenta, and cyan. Those would be the ones you grew up with when you were coloring back in art class. So when you combine colors together, you get different colors. So red and green make yellow. So again, think about the rainbow. What's between red and green? Yellow. It goes red, orange, yellow, green. So between red and green is yellow. So when you add red and green together, your brain says it looks yellow. So if you add red and blue together, you get magenta, and green and blue make cyan. So when you shine these colors together, so red plus green light, if it was a white piece of paper, it'd look yellow. If you take red and blue together, shine them on a piece of paper that's white normally, it would reflect the red and blue there, and that'd be magenta there. Blue plus green, that's going to make it look cyan there. Now, this is important for things like Broadway too, like where if you want to make someone invisible, or if you want to make something look a little more, showcase them, you can use a color that's going to amplify them. I think like a couple years ago we had Shrek the musical, and so we used green light to illuminate Shrek. It really made him pop by shining extra green light on him, and he already reflected the green. It made him pop out a little more. So now color subtraction is the opposite of color addition. In color subtraction, you're trying to take light out, and that's what pigments do, or that's what like your shirt would do. So it's the ability to subtract a certain color. So for example, what if you have a paper that normally looks yellow? If this paper looks yellow, that means when white light, which we're going to say is red, green, blue, hit it, that means that none of the blue comes off, only red and green come off. If we see red and green come off, we interpret that as yellow. So a paper that's yellow has a pigment that absorbs any blue that hits it. So again, white light, right here, red plus green plus blue comes down, hits the paper takes that yellow, therefore red and green come off it, which we interpret as yellow. What if we don't use white light though? What if you use cyan light? Well, cyan light doesn't have all the colors coming down, it just has green and blue light coming down. The paper already takes out blue, therefore, since the blue can't bounce off it, it would look green underneath this. And this is why we can make people look invisible on Broadway. So if someone was wearing a yellow shirt and we had blue spotlights on the stage, we wouldn't be able to see the person in yellow. They'd be dark because the yellow shirt would take out the blue, and they'd become invisible. Again, big idea. White light is all the lights bouncing off. Black light is all the lights being absorbed, nothing coming off of it. So let's do some sample questions here. Let's say magenta light shines on a paper containing yellow pigment. What color do we see? Well, magenta light is actually what two colors? Magenta is red plus blue light. All right, so if we take red and blue light and we shine onto a yellow pigment, what does yellow subtract? Yellow subtracts blue, therefore what we have left? Red light. We would see that paper would turn red under magenta light. If we take yellow light shining on the paper containing red pigment, what do we see? Yellow light is actually red plus green light. Well, what's the red take out? Well, red actually takes out everything that is not red. It takes out blue and it takes out green. What do we have left? Well, since yellow light has red, we're going to be able to shine the red back off of that. What if you have yellow light shining onto a blue piece of paper? Yellow light equals red plus green. Blue pigment would be only reflecting blue and absorbing the rest. It would absorb the red and the green. So let's subtract the red, subtract the green. What do we get? We get nothing left over, which we interpret as black.